Okay, for the next problem statement, this one related to composite wall. Alright, so for the question given to you, a cork slab with 10 centimeter thickness has one face at negative 12 degrees Celsius and the other face is at 21 degrees Celsius. If the mean thermal conductivity of this cork at this temperature range meaning that in between 21 degrees Celsius up until negative 12 degrees Celsius, if the mean thermal conductivity for this cork in this temperature range is 0.042 joule per meter second degree Celsius, then what will be the rate of heat transfer through 1 meter square wall? Okay, so for this particular problem statement, this one is a very straightforward problem statement whereby you just need to apply the use of equation Q equals to Ka delta T over X. Alright? Okay, so one side of the face, this one is 21 degrees Celsius on this particular side of composite wall. So T over here is 21 degrees Celsius, whereby at this particular side, this one is T1 and this one is T2. At the other side, this one, the temperature is negative 12 degrees Celsius. Okay, so it is given the thermal conductivity, the K, this one is K, okay, is 0.042 joule per meter second degree Celsius. Alright, so 1 meter square, this one is the thickness, AX. Okay, so these are the given values from the problem statement. So delta T, where do you get this delta T? 33 degrees Celsius is where delta T is equivalent to 21 minus by negative 12. Okay, so you will be able to get 33 degrees Celsius. Okay, so just apply the use of Q equals to Ka delta T over X. Alright, and you will be able to get the value of 13.9 joule per second. Or do you remember that the conversion factor of 1 watt is equivalent to 1 joule per second? And this particular equation, this particular answer can be expressed as 13.9 watt as well. It is not wrong. They are the same thing, but you need to just select one. It's either this one or this one. Just select one unit only. Do not use both unit, just one unit only. Okay, and then this one is another example of single composite wall. It is given for the at one face, the T1 is the temperature at one face is 20 degrees Celsius and the temperature at the other face is 40 degrees Celsius. Thickness is given at 2 centimeter. Thermal conductivity is given at 17 watt per meter Kelvin. So you need to get the value for Q. Alright, the A given is 1 meter square and you need to use the equation again, Q equals to Ka delta T over X. So you should be able to get the value of 1.7 times by 10 to the power 4 watt. Okay, why watt? You need to know where you are going to cancel out the unit. Okay, for example, this one, K, the unit is watt per meter Kelvin. Okay, and then you have A. The unit is meter square. Alright, and then you have delta T. Delta T is only one single unit. Okay, this one is Kelvin. And then it will be 1 over X. What is the unit for the X? X is meter. Okay, from centimeter, this one you need to convert to meter. Okay, so this one is where you can cancel out the unit. Meter, this one, so meter you can cancel out, and then Kelvin and Kelvin, so you only left with the unit of watt. So that's why Q is in the unit of watt. Now we move on to heat transfer by convection. film heat transfer coefficient and overall heat transfer coefficient. For this particular topic, subtopic, this one involving with the film heat transfer. Film heat transfer meaning that if let's say I have one surface, for example a bowl. I have a bowl that I heat up. This one is the air passing. Okay, this one is your bowl and it is boiling. Okay, so you have the heat here. So this air will pass through and this is the wall of your pot or your bowl. So the film heat transfer will be the temperature in between these two surfaces. The surface of the bowl as well as the surface of the air. Alright, so that is the film heat transfer. Okay, so this one you need to understand. What does this mean? Okay, so convection heat transfer is the transfer of energy by the mass movement of groups of molecules. Alright, it involves either with the air, the molecules of air are moving, the molecules of water are moving during the heating process, during the cooling process. And probably for the air, the movement of the air are being circulated by using fan. So that's why they are convection method. Okay, so for this convection heat transfer, they are restricted to liquids and gases as mass molecular movement cannot occur in solid. Of course, when you have wood, for example, can you move the molecules of wood? Of course, no. The movement of the molecules only apply for the liquid and for the gases. It cannot be mathematically predicted as easily as can transfer by conduction or radiation for this particular convection. So basically the study for the convection is based on experimental results rather than the theory. Okay, so we move on to surface heat transfer. For surface heat transfer, it is the rate of cooling of the surface of a solid whereby it is being immersed in a colder fluid is proportional to the difference between the temperature of solid surface and temperature of cooling fluid. Alright, for example, just now I've mentioned about the cooking pot or the bowl. So this one I give you another example. Let's say I have this particular tubing. Okay, this particular tubing, your liquid product is moving. Okay. And then there's another tubing outside. This one is the cooling water or hot water. Okay, for example, this one is hot water, for example, because we want to have a heating process for the liquid product. So what does it mean by this difference of this particular thing, this temperature of solid surface and temperature of cooling fluid? So this one, this particular part, okay, along of this tubing, this one is the surface temperature, okay. Surface temperature between the hot water and your cold product. Alright, right now we are going to try to achieve a heating process. So your product is colder, the temperature of your product is lower compared to the hot water. Okay, so according to Newton's law of cooling, it is being expressed by the equation of Q equals to Hs Ta minus by Ts, whereby Hs is equivalent to Kf over Xf. Hs, what does it mean by Hs? It is a surface heat transfer coefficient. Ta is a temperature for the cooling fluid. Ts is the temperature of solid surface. Kf is the thermal conductivity for the cooling medium. And Xf is the thickness of surface film of cooling medium. Okay, so for example, if let's say I want to achieve a cooling process. So the hot water just now we replace with cold water, for example. Okay, cold water. Again, the temperature difference is in between these particular surfaces. because it involves with your cold water, your cooling medium, and your product. Alright, it doesn't matter where does this cold water or this particular liquid product is being placed. Is whether they are at the outside tubing or inside tubing. It will be the same thing, whereby this will be the surface temperature that we are going to be interested with. Okay, this is the surface film, this one. Alright, so if let's say we are dealing with several layers of material, then we need to use the equation of Q equals to A delta T 1 over HS1 plus X1 over K1 plus X2 over K2 plus how much of your material involved. Okay, this one is how much the material involved. If let's say you have up until 4 materials, then it will be 4. If let's say you have 3, then it goes up until to 3 materials. Okay, and then you need to close the equation by 1 over HS2, whereby 1 over U is equivalent to 1 over HS1 plus X1 over K1 plus X2 over K2 plus 1 HS2. So this particular thing, this particular part is actually 1 over U. Alright. So for HS1, HS2, this one is surface coefficient on either side of composite slab. X1 and X2, this one is thickness of layers which making the slab. K1 over K2 is the conductivities of layer for the thickness of the material of X1, X2, and how many materials that you are going to deal with the problem statement given to you. Okay, the heat will pass through the surface, then will passing through the various elements of composite slab, and then it may pass through a further surface film. So in order for you to calculate for several materials, this one we have, for example, slab. Okay, and then we have another material, then we have another material like this. So this one is several materials, several slab. So you cannot use the simply equation of a single composite slab. This one encompasses of several slabs. So you need to use the equation of Q equals to UA delta T. And this particular U is 1 over, okay, 1 over 1 per HS1 plus X1 per K1 plus X2 over K2 plus how many materials that you are going to deal with plus 1 over HS2. So this one is Q equals to UA delta T. Alright, if you look at the previous example, this one is Q equals to A delta T over U. But we want to put this U at the top part, so that's why the equation has become like this. Alright, so 1 over U is equivalent to 1 over HS1, the one that we have mentioned in previous slides. Okay, previous slides, please look at the previous slides. U is the overall heat transfer coefficient. Because right now we are going to deal with several composite slab, we are no longer dealing with a single slab. UA is the overall conductivity. When we talk about UA alone, this one is overall conductivity. If 1 over UA, this one is the overall resistance of the material. HS1, HS2 is the same thing, is the surface heat transfer coefficient for each side of composite slab. Okay, this one. Okay, this one is one side. For example, this one HS1 and this side is HS2. Alright. We don't consider for the center material. We are more concerned on the outside and the inside part of the composite slab. Alright, and then X1, X2, this one is the thickness of the layers that making up the slab. K1, K2 is the conductivities of layers of thickness, X1, X2. HS is the convection heat transfer coefficient. Okay, this particular HS, this one. is the convection heat transfer coefficient. When we talk about this HS, alright, this particular equation always apply whenever there is a presence of fluid. Okay, when I talk about fluid, have you heard about fluid? When I talk about fluid, this one involving with gas, gas is considered as fluid, liquid, liquid and powdery material that behaves like fluid. Okay, powdery material, for example, flour. When you pour flour, you can see that the movement of the flour is almost similar like pouring water. Okay, so when we talk about convection, it's always dealing with fluid. Okay, now we move on to problem for composite wall. For stainless steel panes, calculate the rate of heat transfer across two stainless steel panes which are separated by 0.6 mm layer of air, as shown in figure 1 below. This is figure 1. The thickness of each pane is 1.6 mm. The heat transfer coefficient on one side of the pane is 30 degrees Celsius. At 30 degrees Celsius, the heat transfer coefficient is 2.7 watt per meter square Kelvin. And the heat transfer coefficient on the other side of the pane at the temperature of negative 22 degrees Celsius is 11.8 watt per meter square Kelvin. Thermal conductivity of stainless steel and air are 21 watt per meter Kelvin and 0.04 watt per meter Kelvin respectively. Okay, so we assume the area of this system is 1 meter square that we are going to calculate. Alright, so now please take a look for the problem statement. Okay, we have two stainless steel panes. Okay, and this particular stainless steel pane are being separated by 0.6 mm of air. Okay, as shown in this particular figure. So if let's say this one is one side, this one is stainless steel 1, this one is stainless steel 2, and this is air. Okay, air is passing through this system. Alright, so both panes, they are having similar thickness. Okay, their thickness is 1.6 mm. And this one also is 1.6 mm. They are having the same thickness. Alright, whereby the thickness for the air, this one is 0.6 millimeter. Okay, can you see that the unit is being given in millimeter? Alright, so what you need to do for this particular unit, you need to convert to, from millimeter, you need to convert to meter. Okay, heat transfer coefficient on one side of the pane, heat transfer coefficient when we have air. Remember, air is a fluid. When we have air, so this particular problem statement goes for convection heat transfer. Okay, so this one is 2.7. When we have air, and then you have heat transfer coefficient. So you need to make sure that you know this particular problem are related with convection. Convection heat transfer. And it is being denoted by HS. Okay, so at 30 degrees Celsius, at T1 is 30 degrees Celsius. Alright, the HS1 is 2.7 watt per meter square Kelvin, and heat transfer coefficient on the second pane, T2, this one is the temperature is at negative 22 degrees Celsius. Okay, so the HS1, this one is HS1, and this one is HS2. Alright, so thermal conductivity for the stainless steel are given. Thermal conductivity is what? Is K, right? Okay, so this one is K for the stainless steel. K for the stainless steel, and this one is K for air. Alright, they are given as 21 watt per meter Kelvin and 0.04 watt per meter Kelvin respectively. Okay, so how are we going to solve this particular problem? Alright, so this one is the information that has been extracted from the problem statement. Okay, can you see that K1 is equivalent to K3? Okay, how come we have a 3 Ks? Alright, again, I will draw here. So, in between of this stainless steel pane, this one is stainless steel. This one also is a stainless steel. So, in between, this one is air. Okay, so we have this one is the first side of the slab, and this one is the second side of the slab, the other side of the slab. So, this one is K1, K2 is for the air, K3 is for another stainless steel slab. Alright, so remember just now we have the same thickness of the slab for the stainless steel. This one is 1.6 millimeter. 1.6 millimeter. And for the air, this one is 0.6 millimeter. Okay, so since material K1 is similar, because this one stainless steel is being denoted by K1, material number 3 also is stainless steel, so that's why their thermal conductivity are the same at 21 watt per meter Kelvin. Okay, but then for K2, K2 is for the air, K2 is 0.04 watt per meter Kelvin. Alright, and then this one is X1, 1.6 millimeter, this one is X1, X1, and then we have this one, X2 is for the air, okay, and then this one is X3, 1.6 millimeter. So can you see here why they are being 1.6 millimeter? X1 equals to X3, alright, and just now I've mentioned to you, please convert the value into meter. Okay, the same thing goes to X2. The thickness of X2 is 0.6 millimeter. You need to convert to meter as well. Alright, at one side, for material 1, the HS is 2.7. Okay, this one HS1 is 2.7 watt per meter Kelvin. Watt per meter square Kelvin. And then for material, another material on the other side, this one is HS2, right? This one is 11.8 watt per meter square Kelvin. Alright, so since we are going to deal with several slabs, okay, we have stainless steel slab at one side, another stainless steel slab at one side, and we have a slab of air. So you need to use equation of Q equals to UA delta T. Do not use the equation of Q equals to KA delta T, because Q equals to KA delta T is meant for the single slab, single composite wall. For U is always related with several series of tubing or walls. But then of course the use of U, you need to know whether this one is for tubing or this one is meant for composite wall. Alright, for tubing, the equation is different. For composite wall, the equation is different. Okay, so you need to know how to use this particular U for every situation, every condition. Alright, so now since we are going to apply Q equals to UA delta T, and the U that we are going to use will involve with composite wall, whereby it involves with the slabs. So you need to use the equation of 1 over U equals to 1 over HS1 plus X1 over K1 plus X2 over K2 plus X3 over K3, because we have 3 materials here And then you need to close the equation on the other slide with plus 1 over HS2. However, this location of HS1, HS2 doesn't matter whether you want to put it to the front or this one at the back. It's up to you because this one is just a matter of plus. So the answer will be the same, but you need to make sure that you put the correct value into the correct equation, into the correct denotation. Okay, for example, do not miss out this particular K. Okay, for K, the unit is watt per meter Kelvin. When we talk about heat transfer coefficient, surface heat transfer coefficient, HS2, this one is watt per meter square Kelvin. Can you see the difference is here? Meter square and this one is meter. K is per meter. HS2, HS1 is per meter square. Alright? So these are the difference when you want to plug in the values. Although you know the equation but you do not know where to put the value, then your answer might be wrong as well. So please be careful with that. Alright, so this one we have listed all the values. So just plug in the values into the equation. And this particular value, 0.465, this one is meant for 1 over U. Alright, so how do you want to get the value for U? U equals to 1 over 0.465. You need to transfer this value. U is going up over here, then this particular 0.45 need to replace at the position of U. So at the end, for the calculation of U, you should be able to get this particular value, 2.15. And this particular unit, okay, remember, this one can also become as watt per meter square Kelvin. Okay, U is associated with watt meter square. Alright, this one we have joule and second. Just now I mentioned 1 watt equals to 1 joule per second. So it's up to you which of the unit that you want to use, but you need to select only one unit. You do not need to write both units with the same answer. Alright, so now rate of heat transfer is Q equals to UA delta T, and the area we assume is at 1 meter square. So just apply the equation Q equals to UA delta T. Then you should be able to get the value of Q as 111.8 joule per second, or this one is also equivalent to 111.8 watt. Okay, and basically this type of question will give you around 10 marks. Right, now we move on to heat equation and application. Examples of natural convection in food industry. For convection, we have two types of convection, if you remember. Okay, so for natural convection, the retorts which may be vertical or horizontal cylinders are exposed with or without insulation to cool in ambient temperature. And then for the second condition, food is placed inside a chiller or freezer store in which circulation is not assisted by fan. You have a chiller or a refrigerator or freezer, but then those freezer and chiller are not equipped with fans. Then the cooling process of the food product inside the chiller or inside the freezer is applying the condition of natural convection. Alright, and then the third example is a food is placed in oven without fans, and afterwards the cooked material is being removed to cool in air, meaning that you just left the food to be cooled down at room temperature. So that one is natural convection. Okay, for natural convection, this one is more complicated compared to forced convection. Okay, for natural convection, the rate is depend on the first one, the physical constant of the fluid. Okay, second one, dimension of the system. And the third one is temperature difference, delta T. Last one is gravitational acceleration, G. Under physical constant of fluid, you need to know that it is also involving with the density of the liquid, of the fluid, viscosity of the fluid, followed by thermal conductivity, the K of the fluid that you are going to deal with, specific heat at constant pressure, and last but not least is the coefficient of thermal expansion, whereby it is known as beta, for which gases equals to 1 over T by Charles' law. Okay, so the second factor for this natural convection rate, a part of physical constant, the second factor is dimension of the system. In this one involving with the diameter as well as the length of the tubing or the system itself, and then followed by temperature difference, the delta T, what will be the temperature difference between one side to another side. Last but not least is gravitational acceleration, G, because density differences acted upon by gravity that create circulation. Okay, when we cool down our food products by using natural convection, basically we are depending on the gravity as well as the natural environment at that particular area. So some of the particles might settle at the bottom. This is due to gravitational acceleration. Okay, for natural convection equation, this one, the heat transfer rate are being expressed as Hc. Okay, just now is Hs and this time is Hc, whereby Hc is for convection heat transfer coefficient. And for general equation for natural convection, this one we are going to deal with Nusselt number. Okay, Nusselt number equals to Hc d over K, whereby this one is involving with K times by Prandtl number to the power of K times by Grashof number to the power of M times by the length of the tubing divided by the diameter of the tubing to the power of N.